Hello again. Time for the other part of NMR, possibly more important than the carbon-13 NMR in that it tells you so much about something that's quite difficult to locate chemically, which is where are hydrogens. Proton NMR does it. I call it Proton NMR, I call it hydrogen NMR. It's hydrogen 1, odd number. Remember, it's got to have an odd number of nucleons. Standard hydrogen, 1 proton, nothing else in the nucleus. That makes it an odd number. So we call it Proton NMR because a proton is a hydrogen nucleus, which is what we're looking at. NMR, same idea as before, nuclear magnetic resonance. TMS features again. It's the zero marker from which everything else is compared by how far away from it is in terms of to the left, which means it's less energy. Then environments comes in again. Same idea. Look at the way that the structure of the molecule allows things to be identical or not identical, going both ways from where you find it within a molecule. If there's any difference, the environment is not the same. It might be very similar, but it's not the same, and therefore it will occur at a slightly different chemical shift. So the idea of environment runs again. So there are lots of similarities, therefore, between the NMR from carbon-13 that we did and the NMR with proton, and one massive difference thing. We'll come to that in just a moment, well, after we've been shortly. So, same idea, the integration, which is the area under the peak, because the peaks are these really narrow triangles. The integration counts the number of hydrogens, and so therefore somewhere around what you have will be a representation of how big it is. Logical deductions. Yeah, you have to do this. What does it mean? What does it tell me? What can I piece together with all the other evidence that I've got about the structure of an unknown chemical? Because pretty much the entire basis of questions is, here's an unknown, here's a load of evidence, of which Proton NMR will be quite as likely as anything else one of the pieces of evidence, and as a result the deductions you make give you evidence towards an identification. So the use in questions is, it's part of a collection of information that you have to work through, and you have to present your thought processes and propose structures and check that they agree with all the evidence, and if they don't, you're probably closer than you do come up with an isomer, most likely. Chemical shifts are smaller. Chemical shifts only go up to 12 with Proton NMR. That's because the number of electrons around a hydrogen is far less than those around a carbon, so therefore the effect that those electrons have on the absorption of the radio waves in the nucleus to flip the magnets is much less detracting, so therefore you have smaller chemical shifts. 12 is the highest you see. You will need your data sheet. You will need your exam board data sheet because it will have the values of chemical shifts, 0 to 12 for hydrogen, that we are going to need. Now, there is one massive difference. It is caused by an isotopic abundance thing related to carbon-13. Carbon-13 is a 1% approximately abundance of carbon. So it has only a very low incidence within molecules. So therefore, you just see the single peaks. Proton NMR, almost all hydrogens are proton hydrogens like this, and therefore they will be very common, and therefore there's a difference, and it's done with a thing called high resolution NMR, and the protons affect each other from next door locations. So that's a really important thing. It's called spin-spin coupling, and you have to understand how it works. In this video, that's one of the things that we will do. So we're going to clean the board and get ready for the next part of the video, and I will see you in a moment. Okay, two types of Proton NMR. low resolution. Now, low resolution means you haven't turned up all the whizzy-bang stuff in the machine, I suppose you could say. And so what it looks like is it just looks like single peaks, just like you would find in the carbon 13 NMR. So you would have a single peak and it would say next to it something like a 3 to say it's representing 3 hydrogens. Sometimes you see that with a thing like that. This very much depends on what the print of the NMR spectrum looks like. But that would represent it saying 3 hydrogens in height, or at least a height of 3 compared to something that has a height of 1. Now, low resolution, all the NMR spectra would look just like carbon 13 NMR, except that obviously, like I said before, the shifts values will only go as far as 12. Not really what you see very often. Most of the usefulness of Proton Nmr is in high resolution, and most of the A-level questions involve high resolution. So high resolution, you get what's called spin-spin coupling properly. I've written down here sometimes how people refer to it differently. Spin-spin coupling is also sometimes called spin splitting because of what it does. So these are supposedly equivalent, so you would then see next to that a 3 to say that represents 3 hydrogens worth. But you can see that that has been turned into that. This is the splitting, where one peak has been split in this case into 3. It's not always 3. Other numbers are available, terms and conditions apply. Well, very much so. So you get this kind of arrangement where you get what would have been one peak turned into a number of peaks. Now the cause, if we are looking at these hydrogens here on the end of that molecule, they're all the same because the CH3 group, the 3 hydrogens are equivalent. That's why I've said it's 3. But what happens is these 2 hydrogens next door, under high resolution, will affect those 3. And therefore they cause it to split. Now we'll come to all the rules about it shortly. That'll be the next thing we do after this. But so those ones will be split by those. Conversely, these ones will be split by those. But this molecule is quite useful because it shows us one other thing, is that this one here doesn't split, and the reason is it's got oxygen or nitrogen. Now oxygen, almost all oxygen, is 16, even number of nucleons. It doesn't allow coupling to go through it. So the coupling with the carbon must be because of carbon 13. Are you taking notes? Have you thought that you should be taking notes? Are you going to stop this video, rewind it and make your notes? Because you should do. You know it. So just to recap very briefly there, these hydrogens will be split by these. These hydrogens will be split by those. We'll come to how that all works shortly. This one on the end here, because of the oxygen, and it would be the same if it were with a nitrogen, cannot couple through, and therefore this one cannot be spin coupled and split up into multiple peaks. It will be a single peak. Now we'll come to all the ins and outs of all of that very shortly, but I need to get the board ready for some rules and then some examples. See you in a moment. Okay, the rules. You can see we've got 4. I suppose really that one could be number 5. But first one is something I said already, no coupling through oxygen and nitrogen, so we don't get any spin splitting either side of and from hydrogens either side of a nitrogen or an oxygen. OH group, amine group for instance. You only couple to one carbon. Now it can be left to right, it can be either side. So if you go left and right and find hydrogens, they will all mess with the ones in the middle and cause them to split. So if there were 2 on the left, 2 on the right, and you're looking at 1 in the middle, it will get split by 4 on the other side. CH2 on both sides. Identical hydrogens will not split each other. Yeah, you need to write this down. You need to stop the video and write this down. Pause at some point during this. So identical hydrogens cannot split each other. Non-identical hydrogens will be doing the splitting, subject to this, of course. And then we have the names of what we will be calling the various splittings. So if you get a single peak, it will be termed a singlet, not an item of clothing I would like to point out, especially you don't want to be seen in one of those. Singlet, one peak. Two peaks, or a double peak, they'll be the same height as well, because the ratio is 1 to 1, it would be called a doublet. Again, an item of clothing you don't want to be seen wearing, very, very Tudor-esque. Three, unsurprisingly, is a triplet. It's a sort of musical thing going on from here onwards. So a triplet is, actually no, it would be a trio, wouldn't it, musically? But the ratio will be 1 to 2 to 1, so the middle one will be twice the height of the ones on the outside. If you've got 4 peaks, it will be called a quartet, and the ratio will be 1 to 3 to 3 to 1, so it'll be, the 2 outside ones will be short, and the 2 middle ones will be 3 times the height of the outside ones, or 3 times the area underneath the triangle. But the number next to it will represent the integration of all of the peaks in the little cluster to tell you how many hydrogens it came from. Once you get past 4, most A-level courses call them multiplets. So 5 would be a quintet, 6 would be a hextet, 7 would be a heptet, and 8 would be an octet. But in reality, multiplet is the name. And if you had a quintet, for instance, the ratio would be 1 to 4 to 6 to 4 to 1. Now, if you're mathematically minded, you might now recognise what's going on here. Because if I put that 1 there, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4. Do you recognise that? Do you? Pascal's triangle. That's where the height of the peaks comes from. It's about combinations of magnets flipping in different combinations and how many different ways to do it there are. Right, and the last thing is how do you determine what these are? That's not no split, that's the number of splits. The number of splits is called the n+1 rule. Really important you have an idea about this. So n+1. So an example, if there were 3 hydrogens next door, now if you think back to that molecule ethanol we were looking at, if we took at the CH2 in the middle of the molecule, the CH3 on the end is 3 hydrogens. 3 adjacent hydrogens, n+1 rule means 3 plus 1 is 4, so you'd get a quartet. If there were 2 adjacent hydrogens, this is the CH3 on the end of ethanol for instance, 2 adjacent hydrogens, 2 plus 1 is 3, you get a triplet. So in the NMR you would get a quartet and a triplet and a singlet for the uncoupled OH hydrogen. But we'll go through that kind of thing with some examples. But I need to get the board ready for those examples. And you need to make sure you've written all this down. So if you're going to pause it, now might be a good time to pause. And I'll see you after the edit. So 2 very straightforward examples, or 2 relatively simple examples. In the preparation of the board, we were joined by 2 fluffy guests who may make a noise or 2. They were sleeping just now, but they've woken up. Yeah, it's the same 2 as before. The NMR kittens. So, example 1, ethane, CH3, CH3. CH3 next to CH3 when you go that way, CH3 next to CH3 that way. All the hydrogens are the same. They're CH3s next to CH3. So in low resolution, you get a single peak. Now, because identical environments do not split each other, there will be no splitting even found in the high resolution for ethane. So it will be 1 peak, integral height, it'll have a height of 6 because there are 6 hydrogens. Example 2, propane. Altogether more complicated because of the difference. Well, not massively more complicated. CH3 on the end are the same. because they are CH3 next to a CH2 which is central. So that is different to that, so we get 2 peaks. And they will be in the ratio of 6:2, or 3:1 if you reduce it down. In the low resolution, we're not going to go on about low resolution very much, because almost, like I said, almost all questions are high resolution questions. So 2 peaks. So when you get to high resolution, there'll be 2 sets of peaks, 2 little clusters. And because of the nature of high resolution NMR, these ones will split, the CH2 in the centre will split the ones on the outside, and the ones on the outside will split the ones in the centre. This is what happens. There are 2 to consider, I've called them A and B. So the CH3, this is the CH3 on the end, is split by the CH2 in the middle. So the CH3 on the end, 2 in the middle, 2 plus 1 is 3, it will be a triplet. Integral height, well it will have a height, it will be the one that has a height of 6. Just like in the low res. The CH2 in the middle is split by, there's a CH3 to the left and to the right, that makes 6 hydrogens. 6 plus 1 is 7. 7 peaks, we don't give a name to, we just call it a multiplet. So it's a multiplet, and it'll have a height of 2 because there are only 2 hydrogens in that. So much more complicated. In terms of the chemical shifts, they'll all be quite small chemical shifts because they are the chemical shifts of the alkyl groups, which are 0.5 to 2 approximately. And there we are. I didn't do methane as the most simple example because obviously all the hydrogens are the same and the height will be 4. But we'll get on to slightly more involved molecules, and we'll see how it all unfurls. And eventually, not long actually, we'll ask you to have a go at predicting what will happen. And see you when I'm ready for the next examples. Okay, example 3. Again, a little more complex. That's the dishwasher doing what it does. CH3, CH2, and then a carboxylic acid group. Carboxylic acid group being here, if you're not sure. So 3 environments. I've called them in order A, B and C as we go across. Letter them in any other order if you want, but may as well stick with what I've done. So we need to look at what happens. So there goes the dishwasher again. The 3 peaks would give you, firstly, 3 peaks in low resolution hydrogen NMR or proton NMR, and they will be in a ratio of 3 to 2 to 1 in terms of height. So 3 being this one, then 2, then a single one for that. And in high resolution, there is some splitting to consider. So CH3 on the end I've labelled A. It's split by the CH2 next to it. 2 hydrogens plus 1, 3 is going to be a triplet. Chemical shift values are going to be between 0 and 2. We're not going to be able to predict exactly what that value is when we do predictions. We're just going to be able to estimate which range it will be in. This is why you needed the data sheet, because in the data sheet it says there's a little block for different environments and what they will be. The annoying thing is that if you look at it, OH groups and NH2 groups and NH groups, and they have such a broad range because the environments around them make such a difference that they've just got to be a little stripe across the whole thing, which is really quite disappointing. It's not very precise when you look at OH hydrogens or NH2 hydrogens. However, this one, fairly tight range, 0.5. I said 0, but it's kind of 0.5 really. So this is a CH3 with an R next to it. You will see something similar to that in your data sheet. Maybe not expressed exactly like that. When we look at the CH2 in the middle, which is I've labelled B, there is a CH3 to one side. On the other side, it's carbon, and it hasn't got any hydrogens attached to carbon C. So therefore, there's nothing to consider there. So there's just the 3 there. So 3 next door, the CH3 on the end next door, plus 1 makes 4, you'll have a quartet. Now because of where you are in the molecules, CH2 next to the C double bond to oxygen, that has a higher chemical shift, and it's in the 2 to 3 region when you look, and it will be expressed something similar to that. So it will be This one will be away from this one, so it'll be quite clearly a 3 and a 4 nowhere near each other, well, relatively nowhere near each other. And then we get down to the one on carbon C. Actually, I should really have labelled it, I really labelled it wrong. I should have put the C there, because it's obviously the hydrogen we're referring to. So that hydrogen is there, is attached to an oxygen. Oxygen, no coupling, so it's decoupled or uncoupled, whatever word you want to use. It'll be a singlet, but it'll have a very high shift away from TMS, because all the shifts are measured against TMS. You remember what TMS is. If you don't know, go look at the Introduction to NMR video where it talks about TMS. And a very high value, 11 to 12, somewhere in that region. There we are. That's it. Time for me to do one more, and then we're over to you. See you in a moment. Okay, propanone, CH3CO, CH3. I've said it's a singlet. Integration value of 6. Why? Sometimes you will need to explain why. So, why is it a singlet? Well, CH3 next to C double bond oxygen. CH3 next to C double bond oxygen. They're both the same. When you come away from them, you meet the same thing. So, CH3, CA. I'm sorry, there's a visitor who shouldn't be where the visitor is. Excuse me just a moment. Say hello to your audience, young boy. Right, there we are. So, all the hydrogens are equivalent. So, firstly, they're all equivalent. That's why it's an integration value of 6. Secondly, that cannot couple that far away. You could only be coupled onto hydrogens here, but there aren't any. So that isn't split by anything. There's nothing to be split. Same from that, because they're identical. There's no coupling, no spin-spin coupling. Singlet. There we are. Now, next, I'm going to want you to do some predicting, and then we'll see how we go. So, I'll get ready for that, and I'll see you in just a moment. Okay, first one for you to have a go at. Propan 2-ol. Drawn out a slightly awkward structure. CH3, carbon in the centre with a hydrogen and an OH, and then CH3. So, what you need to do, how many environments for the hydrogens, approximate chemical shifts of those environments, so there'll be a range for each one. What will the integration, meaning the hydrogen counting, be for each one of those? And then, for each one, what splitting pattern will you have? Will it be a singlet, a doublet, triplet, quartet, multiplet? And that's all I'm going to say. You need to stop the video and have a go yourself, and then see how you got on compared to what I'm going to say we should have got. So we're going to say pause now, unpause. I hope you did, not just ploughed on, because the whole point of this is that you have to be challenged to think and then have your thoughts confirmed or slightly corrected. So Propan 2-ol, 3 environments. I've labelled them A, B and C. Because of the way that is, that's a CH3 next to an R, that'll have a value, a chemical shift of 0 to 2. The one in the centre, because it's attached to an O, will have a 3 to 4 ppm value. And the one on the end could be anything between 0 and 12 because it's an OH group, annoyingly. So, there's the ranges. I've got them again down there. Integration wise, 6 and 1 and 1. CH3s on the end are identical because it's a symmetrical molecule. So as soon as you get a high value of hydrogen, it usually means there's some symmetry in the molecule, which there is. There's CH3 either side of the centre. So 6 there, 1 hydrogen in the centre there, and 1 hydrogen on the OH, 6 to 1 to 1. Splitting pattern, which is of course particularly the new thing with this. So when you look at the CH3s on the end, hydrogen labelled A, there's only 1 adjacent hydrogen on the centre. It won't couple at all up through the oxygen, as we said before. So those are split by a single hydrogen in the centre. One hydrogen plus one makes it 2, and it will therefore be a doublet. It'll have an integration height of 6. And it will be in that 0 to 2 range, usually 0.5 to 2. Then, the middle one is split not by that hydrogen, because we don't couple through oxygen or nitrogen, but it will be split by the 6 hydrogens, 3 to the left, 3 to the right. 3, that's 6, plus 1, 7, it'll be a multiplet, it'll be a heptet. And it'll be in that 3 to 4 range, and it'll have an integration height of 1. And the OH, not coupled to anything else because of the oxygen, so it's therefore going to be a singlet. It's going to have this randomly somewhere in the 0 to 12 range. You may have it different in your data booklet, but the one that I use at school does have that massive range. Integration value of 1, because it's only one hydrogen. That's example 5. We're going to do the same thing again. I'm going to put a structure up. You're going to make the same predictions. You're going to pause to do it, and then we'll unpause, and I'll see you in a moment. So, your turn again, example 6, but1ene. There's the drawing of but1ene. Same thing, number of environments, approximate chemical shifts for those environments, integration values for the number of hydrogens, and what splitting patterns will you see for those environments. Time to pause, unpause. but1ene. 4 environments. I've labelled them A. These are all the A's. I didn't label each hydrogen with an A, but they're all A. These are B, that's the C, and there are 2 D's on the end. Chemical shift values, A, B, C, D, 0 to 2, 0 to 2, 4.5 to 6, 4.5 to 6. Integration heights, 3 hydrogens worth, 2 hydrogens worth, 1 hydrogens worth, 2 hydrogens worth, so it's 3 to 2 to 1 to 2. And then we get on to the bit that we're really interested in, which is what will the splitting patterns be. So, hydrogens labelled A. 2 hydrogens next door. 2 plus 1 is 3. These will be a triplet. Here they are. N plus 1 is 3. Now don't get the 3 confused with the CH3. It's about how many next door. So it will be these 2 hydrogens splitting it. N plus 1 makes 3. It's a triplet. 0 to 2, like I said before. Integration height. That's a little integral. So that's what you see. Shape like that. Height of 3. Hydrogens B. 3 hydrogens that side, 1 that side. That makes 4. 4 plus 1 is 5. Now 5 would be a quintet in not giving it a proper name, but it would be termed a multiplet at most A-level courses. Again, 0.2, integral height of 2, because there are 2 hydrogens doing it here. It's not about how many, the integral value is not about how many are doing the splitting, it's about how many are in the location, and then you do the splitting from either side, if either side exists. Then, C. 2 on the left, 2 on the right, 4, 4 plus 1, 5, it's again a quintet or a multiplet, but the chemical shift is a larger shift this time, away from TMS, but the height will only be 1, so it'll be a somewhat smaller multiplet of the same number of peaks as this one. And then finally, on the end here, these 2, only 1 next door to split it, 1 plus 1 is 2, it will be a doublet, 4.5, 2, 6, there's the 4 splitting. So you will find 4 peaks. You notice I haven't talked about low resolution because I've really moved on from that. And there we go. Example 7 coming up. Last one like this. I'll see you after I put it up there. So, your turn again. Example 7. Come from the biological area. Glycine, amino acid. There's its structure. I don't know whether you know about amino acids or not. There's its structure. Number of environments, same as before, blah. Predict. So, pause me, and I'll see you after you've had a go. Pause. unpause. Here we are, glycine, 3 environments, A, B and C, 2 hydrogens there, 2 there, 1 there, 5 hydrogens in total. So 3 environments. NH2 group, that long randomness of could be anything, 0.5 to 12. This one in the middle, 2 to 3 because it's next to that. And then, next to that as well, so next to there, so 2 to 3 for that. And then the carboxylic acid, 10 to 12. Splitting pattern, well, A, those hydrogens cannot couple through the nitrogen, singlet. The 2 in the centre cannot couple to those hydrogens or to that hydrogen. This one's too far away, those ones are going through nitrogen, don't couple, singlet. So singlet, singlet. And this one here can't couple through the oxygen, singlet. So all 3 are singlets. And that just summarises the chemical shifts and the integration sizes there. So you would just have, in high resolution, 3 lines, because there is no spin-spin coupling taking place in glycine. That's it. Next example is very different. So I will see you once we're ready for it. Okay, example 8, slightly different now. Up on the screen, after I finish speaking, will come an NMR spectrum. Now the question is really straightforward. It's, is this the NMR spectrum, the proton NMR spectrum of butanal or butanone? Now the answer actually is very straightforward and very simple, but it's not about just what's the answer. The answer is very simple to get. It's also about how you answer this kind of, because it will be a multi-mark question. There will be a whole number of marks available, mostly for doing this, and then some for doing this bit. So you need to be able to express how to analyse an NMR spectrum. Now, it's the reverse of what we've been doing. We've been giving the hydrogens letters and then saying what they would be. Now we're going to turn it inside out, and you're going to look at the NMR spectrum, put letters on the NMR peaks, and then analyse each peak or peak group at that letter for what it means. Then propose a molecule. So what you do is you analyse it, you propose. Now the propose is very simple because it's one of those 2. You propose which one you think it is, and you predict what that will have. If it agrees, you have solved the question, the problem. If it doesn't agree, you go back and it must be the other one in this case. I will answer, when I do the answer, I'll do both, and you'll see why it's one and not the other. So the spectrum will come up now. You need to pause it, and then you can write down your analysis of it on the screen. I will see you after you've done your analysis and you've unpaused me. Having written down what you saw, you should have something along these lines. A, B and C, and I have identified ppm values there, 2.45, 2.1 or 1.0. I've proposed these environments of CH next to a CO double bond R carbonyl, similarly there, and this is just a CH next to an alkyl group. Integral values of 2, 3 and 3. So therefore that has to be CH2 C double bond oxygen, that is CH3 C double bond oxygen, and that is CH3 because of the 3 to next to a CH2. Now when you look at that there, 2 plus, if we're looking at this hydrogen, these are the hydrogens we're looking at, 2 next to it, 2 plus 1, triplet, that's a 3. Here it's a singlet, because this can't couple through that, so everything else of the molecule must be this side, so that's uncoupled, that makes it a singlet. That CH2, well, if that's that CH2, it's next to a CH3, 3, so these hydrogens there, 3 next, 3 plus 1 is 4, it will be a quartet, which is what we're expecting. So when you look at, this is the answer. It's actually quite easy as an answer, because if you then predict for butanal, you'll see it has 4 different environments. So the answer is very straightforward. But what I want you to be able to do is express the analysis clearly but succinctly. So type that kind of sequence of things. Here's a proposed molecule, CH3, CH2, carbonyl, CH3, which is butanone. Sometimes people call it butan-2-one, but it doesn't need the 2 because it couldn't be anything else. and you predict what the splitting patterns would be. So those there, that's a shoddy pen, don't want to write. That's because this pen has got ink in. So those would be a triplet, those would be a quartet, and those would be a singlet. And there are 3 environments, and that is what you saw. I'm going to do, once I've wiped the board, I'll do the analysis. No, sorry, not the analysis. I've done the analysis. This is the analysis. I'll do the prediction for butanal, and you'll see it doesn't match what you've written down for that. But I haven't got enough board space because this is a small whiteboard. See you in a moment. So if we'd have had butanal, which is this molecule, first thing is there are 4 environments. They're all different. 4 sets of hydrogens. We would have seen a triplet, a quartet and a singlet, but there would have been also a multiplet. Now just to run through why that would be, because it is useful to do this just in order to give you more, more practice. That CH3 will be split by 2. 2 plus 1 makes it a triplet. That CH2 will be split by 3 and 2 on the other side. That's 5 plus 1 makes it a hextet, which we just call a multiplet. Those are the ppm values for those. This one here, ppm of 2 to 3. How many is it split by? 2 there, 1 there. It's not coupled through the oxygen, so that one does get involved with those, making 3, splitting it. 3 plus 1, 4, quartet. And this one on the end there would not be a singlet. It would be a triplet. Why have I written that? That's just rubbish. That would be a triplet. So triplet, hextet, quartet, triplet. Not the same spectrum as we saw, so if you propose that, you would predict that and then go, that doesn't match what I've got, so then you propose it must be the other one, and say you've done it. Example 9, I'm not going to give you any clues what it is. You're going to have to use the spectrum and predict what molecule it is. So I'm not even going to write anything on the board, I'm just going to say example 9, which will come up shortly. The spectrum, the Proton Nmr spectrum will come up on the screen. You need to pause it and then do your analysis, propose, predict, does it agree? It's a little bit more tricky because you haven't got any, oh, is it this one or this one? You've really got a complete blank canvas. And then I'll be back with the analysis of that spectrum and yeah, see how you got on. Analysis first of all. 5 environments, because there are 5 sets of P's. I've called them A, B, C and D, E. And there's my ppm readings. There's the type of grouping you've got. I've gone for hextet and quintet because it does unlock information about the molecule. So hextet means that there are 5 hydrogens. That's a singlet. I'm going to say with that value, with an integration of 1, it can't be NH2, so it's likely to be the OH because of where it is, making it an alcohol. Okay. Then you've got a quintet, meaning that there are 4 hydrogens, integral value of 2, and then there's a doublet, which is only therefore going to be 1 hydrogen next to it, but it's 3 hydrogens in height, so there are 3 hydrogens in that environment split by 1 next door. And similarly triplet in n equals 2 with a height of 3. Now what that means is that what you are seeing is this hydrogen, 1 hydrogen's worth, which is why the integration is 1. 5 hydrogens means it has to be mid-molecule to get hydrogens on either side to sum up to 5. The high value is because it's attached to the oxygen, it's actually attached to an OH, but the hydrogen is irrelevant. So we're going to propose it's that environment. That is the OH environment, which I should have written down there, but I managed to write it above it. There we go. The 4 means it's CH3 and CH. Now it could be CH2 on either side. Okay, that would still give you 4. but I'm going to say it's that because of what we said over there. And similarly, CH3 as a doublet, there has to be just a single hydrogen next to it, which is CH. And similarly there, to get a triplet you would have to have this CH3 split by, so these are the hydrogens here, these are the hydrogens you're looking at each time, there, which means the structure that this leads you to is that. And the answer is, it is butan 2-ol. Now that may put you out of your misery, but what I want to do is I also want to do, when you propose the wrong molecule, what happens. So when you do that and you piece the evidence together, you propose butan 2-ol. What you then do is you then go, oh, that will be a doublet, that will be 5, so that makes it a hextet, which you're seeing. And similarly that is split by 4, which makes a quintet. That is 3, split by 2 makes it a triplet. So it matches what you're seeing, everything matches, the right sort of values for shifts, everything fits together, it's butan 2-ol is the answer. Now if you propose that and got it to match, that will be the end of the question. You've proposed a correct answer. Sometimes there are more than one correct answer because of the way the question is worded, but most of the time it leads you to one molecule. What I'm now going to do is I'm going to do it for butan 1-ol, which is the wrong answer, and show you what happens. But I need to get the board sorted for that. See you in a sec. Now, if you'd have proposed butan 1-ol, which looks like that, still got 5 environments, so you would then go, right, I'm going to predict what butan 1-ol would do, and it goes through from, and they're in a bit of a random order because I kept some of the things the same. You would get a triplet, singlet, quintet, hextet, triplet. The doublet, which you had in the actual spectrum, you wouldn't see. You don't get a doublet in this prediction. When you predict what you get, there's no doublet. Hence, without even doing ppm values and environments, immediately you go, no, it doesn't match. And the size of the peaks also wouldn't match, because you haven't got a second 3 height, because there's a 3. But there isn't a second one which you would see in butan 2-ol. So therefore, there's a couple of things immediately would say, this is not right. So the process then, if you propose butan 1-ol, you would then go, it doesn't match what I'm seeing, I'll go for the simplest next isomer, which is butan 2-ol, go through the prediction and it would have come out correctly. And that's, for a multi-mark question, you would have to show your thought processes, really. It's kind of like a detective thing, where you have to write down what you're saying. And if you go through and you get it wrong, it's not, I mean, it doesn't get you any marks, but it's not bad science, because in the end it leads you to the correct answer. Now, there are a whole range of attached questions for you to practice on, because quite frankly, this is the hardest thing about NMR is, at A level, is doing this spin-spin coupling, understanding what it means, what it allows you to interpret. So there are some attached questions, and eventually there'll be some attached answers which I haven't written yet. And there will be, therefore, you practiced. It is quite difficult, and I would suspect some of you might need to rewind and re-watch parts of it to get the understanding and realise how important some things are. But I want you to practice on the questions, because quite frankly, it's all about being able to understand, analyse, express it clearly, and come up with a predicted molecule that is either correct or incorrect, and eventually takes you through to the answer. Thank you for watching. It's been a bit long, but it's really important, but it's also quite difficult. So thank you for putting up with it, and I hope you've benefited from it. I will see you for the last of the NMR videos soon, which is more about bringing together a whole collection of evidence. So different types of spectra all put together, and then you get questions where you bring all that information together. I haven't written that yet, but I will see you for that soon. Thank you for watching. Goodbye.